we've got a giant scale ammeter. In fact, it's actually a milliammeter, which means it can measure a very small amount of current. And over here, we've got coils of wire closely wound up, and in here it says it's around 1,000 turns. And watch what I'm going to do. I'm going to use a magnet, right? And to prove to use a magnet, let's just take another magnet and do that repel. And if you swap the direction, it attracts. So that's a permanent magnet, unlike an induced magnet, which always attracts. So if you swap the pole, it still attracts. Swap the pole, still attracts. So that's an induced magnet. I'm not going to use an induced magnet. I'm going to use a permanent magnet. And watch what happens. So if I connect the coils of wires to my actual very sensitive ammeter, right? And I move a magnet in and out, I get a deflection here. Now, a deflection in an ammeter effectively means that I've actually produced current. And this is the core of electromagnetic induction, right? The production of electricity. Notice that there's no fake science. There are no batteries around here. I'm actually effectively making electricity, right? Previously, we've looked at motor effect, where we use electricity, a bar magnet, and we have a turning effect like a fan. This is called a generator effect. Okay, let's do that again. If a bar magnet moves into a coil of wire or several coils of wires, there's a deflection. And if you move it faster, there's actually a bigger deflection. Notice that if you take that same bar magnet and you leave it here, static, no movement, there's no deflection, so you don't make electricity. And that is summed up in Michael Faraday's law of electromagnetic induction, which goes like this. The EMF is directly proportional to the rate of change of magnetic flux linkage. However, this is more of an A-level. So when you get to A-level physics, we're going to talk more about this. I'm interested in that d by dt, which means that the field has to constantly change. If the field isn't changing like this, I'm not moving in and out, there's no induced EMF, right? Moving it in and out, and I do get an induced EMF. And you may notice that when I actually do this in and out movement, the needle goes left and right. Left could be negative, right could be positive. I'm actually producing an alternating current, okay? And this is very, very similar to this little demonstration that we've got over here. So these coils are now in the same fashion, and they are made up of copper. So, and it's collected directly to the mains. Rather than me trying to change the magnetic field by moving in and out, but I could use something else that has a change in magnetic field, and that is an AC. And watch this. So this is plugged onto the mains over here. Once I turn it on, right, watch what happens. The bulb lights up. Now the bulb is connected just to a bunch of wires. There's not a battery again, and it's actually not connected to anything here. The wires are here. So how come am I getting electricity flow through this light bulb? And watch it. Actually, what's happening, as I press this button, it closes the switch, makes a complete circuit, and there's a current that flows here. However, this is connected to the mains, which means that the voltage is also changing. And if the voltage is changing, the magnetic field around it is changing. So rather, it gives me the same effect as this in and out movement. Changing magnetic field from Michael Faraday's law states that there's an induced EMF, right, if a wire cuts across a changing magnetic field. Remember that changing magnetic field? It has to be changing. Again, if I leave it in here, there is no induced EMF. But if there is movement, the field is changing. And you can see that, changing. One last thing that we're going to talk about is Lenz's law. So Michael Faraday's law looks like this. And you can put a little n here if you want to put a little n. If you do increase the number of turns, the induced EMF is higher. Michael Faraday, Lenz's law puts a little minus. What does that minus mean? That minus shows the direction of that induced EMF. So watch what happens. As the bar magnet approaches, it deflects to the left. As the bar magnet recedes, it deflects to the right.